All right, today we're going to talk about the rational functions. This is the last two sections in chapter 2. And there's really only three things you have to do. You have to find the domain of a rational function, which in fact is part of the second thing, where you use that to find your vertical asymptotes. And then you'll use your relationship between the numerator and the denominator to find your horizontal asymptotes and your holes. Okay? The last thing you're going to have to be able to do is to sketch these functions. Okay? So we are actually going to combine 2,6 and 2,7. We're going to start by doing 2,6, and then we'll finish up the notes with how to do 2.7. Okay, so what does rational mean? A rational function is just a fraction. That's all it is. It's just a fraction. Okay? And so you have a polynomial on the top and a polynomial on the bottom. It doesn't even have to be a polynomial. It can be a monomial. But you have a fraction. And what you're going to do is use the relationship between the top and the bottom, the numerator and the denominator, to figure out what everything is. Okay? The number one rule is that the denominator can never, ever, ever, ever be 0. This becomes super duper important because that's also going to help you with your domain, and it's also going to give you your vertical asymptotes or your holes. Okay, so keep that in mind. The same rules that were true back in 2nd and 3rd grade are going to be the same rules we follow today, only it's going to look slightly different. Okay, so here are some graphs of rational functions, and a couple of things I want to point out. The first thing, if you look at this first graph, you'll notice that it is headed this way. But it's never actually getting to this value. It's never going to actually touch that. The second thing I want to point out, I'm going to put this in red, both of these graphs are approaching this. Okay? So now I'm going to come over here, and I'm going to do the same thing. And I'm going to say, okay, these values here, if we look at the denominator, x equals 2. Approaching, but never actually getting. I know it looks like it gets there, but it does not. And the second place is -5. It looks like it's getting there, but it isn't. Okay? Now we're going to come down here, and we're going to look here, and we're going to notice that no matter what I do, I am never going to make that 0. No matter what, it is never going to be 0. And notice I don't have any red vertical lines to draw. There are no red vertical lines to draw. Okay, it cannot happen because there's no place that the denominator would be equal to 0. Take a look here. X plus 1. What would make this cannot be 0. Remember, it cannot be 0. So what number would make it 0? And you would go, oh, Miss Collins, silly girl, that's at -1. Correct. Look it, I can draw it in there. Those lines are never going to cross that line, ever. Okay, come down here. Same thing, just looking. It's never going to be good, 1. And it's never going to be -2. Now, I know some of these graphs look like it's approaching there, or touching there, but it can't. It cannot be there. Okay, just graphing issues with my. So it can never be 1, and it can never be -2. Now, this is where it starts to look really ugly when you look at something like this, because you go, oh, Ms. Collins, I can't factor by grouping. I can't factor that. No, you might not be able to factor that right now, but what's going to happen is you're going to be able to factor this one and then see if they have a common factor. Hint, 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 it doesn't go away. Okay? It doesn't go away. Yay, we get to use something else. Okay, so we're going to tackle this one at the end. Just know we're going to come back to that on day 2. We're not going to do that one on day 1. All right, so let's do some of the work ourselves now. Okay, so the 3 things that I want you to do, right? I want you to find domain. And the domain is actually going to give us our vertical asymptotes. Okay, so what we want to do is we want to take it piece by piece, step by step. So I want to take a look at the denominator. And the rule is 2x plus 3 cannot be 0. Okay? This is what I'm going to do when I set up to find my domain. Okay? So at the very beginning, we're just going to take the denominator and we're going to set it and say that it cannot be 0. It's kind of like solving and setting it equal to 0, only we're saying it can't be. So now I'm going to go ahead and do some algebra 1. So my domain is x cannot be -3/2. Okay, that is my domain. X cannot be -3/2. And the reason x can't be -3/2 is if it were, this would be equal to 0, and you cannot have the denominator equal to 0. So when we're talking about that, discontinuous means there's a break in my graph, which means if I wanted to draw my graph, I would have to pick my pencil up. And so what happens at each of these points, I'm putting a lot of stuff together here right now. That means this is going to become a vertical asymptote. Okay, so I'm going to switch back a page because I want to show you. On this page, where the denominator can't be 0, so x cannot be 4, we drew in this vertical dashed line. Vertical dashed line. Imagine if x equals 4, your world blows up, right? No, you cannot be 4. So we draw the vertical line. Okay, we're never going to cross that. Okay, so let's take a look at this option. So now we have a simple x equals 1. Okay, so at this point, I'm still completely disregarding the numerator. I'm only looking for domain. So my domain is such that x, so when I find my domain, this is what I'm doing, that x minus 1 cannot be equal to 0, which means x cannot be 1. That is my domain, which means when I'm graphing at x equals 1, I would have a vertical dashed line. This is going to be what we call our vertical asymptote. Okay, vertical asymptote. Domain restrictions equal vertical asymptotes with a little asterisk. Okay, so now let's get rid of this one. I don't want that one. I'm going to delete that. Okay, so let's take a look at this one. Now notice I just got done saying if the denominator is equal to 0 or domain restriction, we're going to have a vertical asymptote with an asterisk. Here's why. Now when I rewrite this problem, I notice at the bottom is a difference of squares. So we get x minus 2, x plus 2. That's how the bottom is going to factor. Okay? So when I do this, I notice that, okay, so x minus 2 cannot be equal to 0, and x plus 2 cannot be equal to 0. And I notice something here, and I'm hoping you see it as well. I'm going to go ahead and box it in green. What do you notice? Okay, those are the same. And so I can technically wipe it away. I can reduce it, if you will, simplify it, if you will. And by doing that, this right here, while it's still a domain restriction, x equals 2 is going to become what we call a whole. Okay, so just put this off to the side for a minute. So my domain, x can't be 2. This one is going to give me that x cannot be -2. Those are the two pieces for my domain, which means my domain is x cannot be 2 or -2. Okay, and so the way it works is this. I'm going to call x equals 2 a whole, but at x equals -2, that is going to be a vertical asymptote. Okay, I'm using the words today because I want you to see them. I want you to see them because we're going to put it all together. All right, let's do some discussion of vertical asymptotes and wholes. Vertical asymptotes and wholes are all denominator issues. Denominator issues. Okay, so if there is a number in the denominator that we will make it go to 0, we can't have it as our domain. Okay, so when you're thinking vertical asymptote, think of the word domain. Okay, and when you think of the word wholes, think common factor. Okay? So domain and common factor. Okay? So the technical definition says a graph of a rational function has a vertical asymptote, or has vertical asymptotes at the zeros of the denominator when there are no common factors with the numerator. Okay? If there is a common factor, so this is domain, vertical asymptotes are equal to the domain. Okay? And then when we take a look at a whole, we are thinking common factor. These two are equal terms. Okay? So if we have a whole, that means there's a common factor between the top and the bottom of our fraction. If there's just a domain issue, then it's going to be a vertical asymptote. Okay? So before I move on, I want to do an example just to make sure. We can cut this out. Cut. What we can do here is take a look at just an example or two. We just did this one, and we got this. And we notice that we reduced this. That means I have a whole at x equals 2. Okay? Now, I don't know where on the y values that is, but I know there's a whole at x equals 2. So there's going to be a whole at 2 comma something. 2 comma something. We're going to find that later. And then because this is still left in the bottom, x plus 2, so here's what we have now. X cannot be negative 2. This becomes our domain issue, which leads us to a vertical asymptote. Okay? Vertical asymptote. A vertical asymptote looks like a vertical dashed line. Okay? So if we took a look at this one, let's say I had x plus 1, and on bottom I had x squared minus 1. Okay? So immediately you're thinking, oh, well, Miss Collins, you silly girl, that's going to factor. I agree. That's why I chose it. Minus 1. And we say, okay, look, this reduces. So that reduction means I have a whole at x equals negative 1. Right? Because x plus 1 cannot equal to 0. So x cannot equal to negative 1. This is the common factor. We can cross it out. But now this becomes a vertical asymptote. So that means this leads me to a vertical asymptote at x equals 1. Okay? So, oops, sorry. When I do this, this is going to be negative 1 comma something. It's an ordered pair that I'm going to use to graph. And when I do this one, it's going to be a dashed line at x equals 1. Okay? So that's what we're looking at. The second thing we have to talk about is horizontal asymptotes. And horizontal asymptotes become a relationship between the numerator and denominator. And it has to do with the degree of the polynomial. Okay? So we talked about this in the sections 2.1 through 2.4. And we talked about the degree. So odd, up, down, up. Even was up, or down, down. Now we're going to talk about the degree of the numerator compared to the degree of the denominator. Okay? That's how we found, or we are going to find our horizontal asymptotes. So if the degree, option one, if the degree of the numerator is less, numerator is top, is less than the bottom, then you automatically have the answer y equals 0. Okay, so for example, I'll show you a couple. Let's say you had x plus 1 over x squared plus who cares. So you take a look at the leading coefficients. This one's a 1, this one's a 2. 2 is bigger than 1, therefore you have a horizontal asymptote horizontal at y equals 0. Okay? Notice I'm not using x. The x value doesn't matter now. X is only for domain, so we have a horizontal asymptote at y equals 0. That means there's a dashed horizontal line at y equals 0. Here's another example. What if you had y equals 4x minus 12x squared plus 13x cubed all over x to the 4th? Okay? Remember, order doesn't matter, so I look across the top and I find that the largest exponent is right here at 3. I then take a look at the bottom, largest exponent. Since 4 is greater than 3, my answer is horizontal asymptote at y equals 0. Again, dashed line at y equals 0. Okay, so this is option 1. Option 1 is the denominator is bigger than the top, the numerator. All right, option 2, on the other hand, option 2, hey, why are you doing that? Option 2 says if the degree of the top is equal to the bottom. Now, it doesn't matter what that exponent is. The exponent is irrelevant. We're just looking at that as our relationship. But then we are going to be given an asymptote y equals a over b. Okay? A is the coefficient of the top, and b is the coefficient of the bottom. Okay? So it looks like this. Let's say you had y equals 2x plus 7 over x minus 4. Okay, so again, we're looking at the relationship of top to bottom. So you put a box around the leading exponents, and now you take a look and you say, oh, hey, look, this is a 1 and this is a 1. They are equal. So now, final check, take a relationship check here. 2 over 1 means I'm going to have a horizontal asymptote at 2 over 1 or 2. Horizontal asymptote, dashed horizontal line at y equals 2. Okay, what if they're written in the wrong order? For example, 3x minus 7x squared plus 12x to the 4th. Who cares? And then on the bottom, I'm going to go ahead and write 16x to the 4th minus, I don't know, 10x squared plus, I don't know, 12x minus 144. Who cares? Doesn't matter. But we're going to do the same process. So we look across the top until we find our largest degree. We do the same thing on the bottom until we find our largest degree. And then we take those two pieces. And we just want to look at those two pieces. 12x to the 4th over 16x to the 4th. We notice that the degree is the same, so we can get rid of them. They reduce. And now we have 12 over 16, which reduces to 3/4. And that's going to tell us, now keep in mind, this is all in our head. All in our head. Which leads us to our final answer, that there is a horizontal asymptote at y equals 3/4. Okay? So option 1, the bottom is bigger. We go y equals 0. Option 2, they're the same. They're the same. In which case we look at the ratio. And option 3 is that the numerator is bigger, and therefore we have no horizontal asymptote, which means it's going to go on forever. For example, if we had x squared over x, 4x, who cares? Since 2 is greater than 1, we have no horizontal asymptote. Okay? And the reason is, as I reduce this, that's just going to be a line. It's going to go on and on in both directions. Okay? So you can think about it in Algebra 1 terms, but ideally we want to just take shortcuts. What if I had 4x to the 6 minus 12x to the 8 all over, I don't know, 164,000 x to the 7th? Okay? Again, doing the same thing. I'm looking at the relationship for top to bottom. So I look across until I find the largest. I find the largest. And so now I say negative 12x to the 8th over 164,000 x to the 7th. Since 8 is greater than 7, the top is bigger, there is no horizontal asymptote. Okay? And that's true forever. Okay? Forever. In honors pre-calc or in AP Calc, they're going to call those limits. But for now, we just say there's no horizontal asymptote. All right, so now we're going to put it all together. Okay? So for the function, we want to find the domain. So the first thing we're going to do is find the domain. Okay? The domain says take this and set it not equal to 0, which means x cannot be 4. By doing that first, this, when x equals 4, becomes my vertical asymptote. So I'm going to come over to my graph, vertical asymptote, and I'm going to sketch that in. Okay. Now, horizontal asymptote. Horizontal asymptote means I'm going to go ahead and take a look at the ratio of x to x. The degree is 1 to 1, which means they're equal. So now I'm going to look at the coefficients, which is 1 over 1, and I get y equals 1 as my horizontal asymptote. And so at y equals 1, I'm going to put that in. Now, for all intents and purposes, the next step is super easy. I want to choose 2 points. And it doesn't matter where I choose them, because I'm going to tell you, you're going to have reflections or mirror images. Okay? So we're going to use a cheat. I call it a cheat, but it's just common sense logic once I tell you why. I want to choose a point in either here, 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 or here. So an x value from here to here, or an x value from here to here. And then it's going to tell me which of these quadrants I'm going to be plugging into. So what I'm really looking for is an x value to the right and to the left of my vertical asymptote. So the prettiest number to the left of my vertical asymptote is actually 0. So if I plugged in 0, 0 plus 2 over 0 minus 4, I get negative 1/2. So at 0, I'm going to erase these lines right here. At 0, I was at negative 1/2. And I don't want to, because I know what the answer is going to be. But I'm going to plug in one other point just to show you the general pattern. I'm going to go ahead and plug in 1. So I'm going to say 1 plus 2 over 1 minus 4. Now what I'm doing here is I'm plugging 1 in for x. So anywhere I saw an x, I'm going to plug in a 1. And I'm going to get negative 3 over 3, which is negative 1. So 1, negative 1. It turns out the graph is going to go like this. And that means the other piece is going to be up here. And I'm going to cheat and do that every time. So once I know that it's in this quadrant right here, I'm going to just go opposite and sketch in that little piece. I can do test points, but I don't want to. It takes a lot of time. Okay? And that's how I do it. I do not have any holes. Why do I not have any holes? Why do I not have any holes? The reason I don't is because I have no common factors. Okay, so let's take a look at this one. Now this one is going to have a little more stuff for us because we're going to have to factor the top. And we're going to factor the bottom. And the first thing I want to do is look at my domain restrictions. And so if I set each piece equal not to 0. And I want you to do this on your papers. I want you to do this on your papers. I'm going to give you a handout today to do tonight while you watch this video. But I'm going to give you a paper. I want to see this on your paper. So x cannot be negative 3 and x cannot be negative 1. And that would be fine. These are going to give me my domain. That's my domain. But I need to classify them as either a whole or a vertical asymptote. And so what I need to do then is I need to take a look at these two factors and go, hey, x plus 3, I can wipe away. I can wipe away the x plus 3. So if I wipe this away, this becomes a whole. And so now I need to find out where that happens. So I'm going to take that and I'm going to do something with it. And so what I do is I come over here and I rewrite this. X plus 3 over x plus 1. That's my new simplified version. And since x plus 1 is still in the bottom, this right here becomes a vertical asymptote. So I'm going to come over here and I'm going to put in my vertical asymptote. That's my vertical asymptote. I'm going to come back over here now and I'm going to say, hey, what if I plug negative 3 into my new simplified expression? And what I should see immediately is that the top goes to 0, which means that's my point, negative 3 comma 0, negative 3 comma 0, and I put a hole right there. A hole is an open circle. Open circle. Okay? And so I say, okay, but I need my horizontal asymptote now. The last thing I have to do is horizontal asymptote. Now I can look right here for my horizontal asymptote, and I can see that I'm going to get a horizontal asymptote at y equals 1. Or, look, come all the way back to the original and see that. What's x squared divided by x squared? It's 1. If I look at my horizontal asymptote here, I get y equals 1. So it doesn't matter which way I go. So I'm going to go ahead now and pop that in. Y equals 1. And look, this is important. Do you see this hole right here? That means that my graph is going to be here, which also means that I'm going to have a graph like that here. Okay? Now, I put this dot here because it's a mirror image of this one. This one was left 2, down 1, so this one must be right 2, up 1. And so that's just a little kind of trick. Okay, so here's what you're going to do. I have a worksheet for you. And you and your partner are not going to do this because we're doing this note at home now. You're doing these notes at home. Okay, so I'm going to cut that. You are now going to do the worksheet 2.6, day 1. I'm handing that to you today in class, and I want you to do that one tonight for homework after you watch this video. And I only want you to take a look at a couple of them. You don't have to do the whole thing. I'd prefer you do at least 3 so that when you come into class on Tuesday, after the assembly, we can get right into the work. All right? Good luck.